In this unit, we're going to be talking about something called the electrostatic boundary value problems. So in previous chapters, what we've done is we've known the charge distribution in some region. So maybe we knew we had so many point charges at certain locations, or maybe we had some other known quality, for example, a voltage that we knew throughout an entire region. And what that allowed us to do, whether we had the charge distributions or we had the voltage equation throughout the region, we were able to find our electric field. And it turns out that that's not always what's going to be happening in a realistic application. So what we're going to look at in this chapter or in this unit is we're going to consider the more realistic situation of finding our electric field and our voltage in a given region when we only have electrostatic conditions at the boundaries. And so sort of the simplest case, which we'll come back to in a later example, is we could think of a capacitor. So for a parallel plate capacitor, maybe we know the voltage on our two plates, and knowing that, we could figure out our electric field and voltage and a lot of other quantities, as we're going to see later, based on just the boundary values of that electrostatic condition. So we're going to talk about a couple different ways that we can do this. The first one is primarily what we're going to focus on. The second one we're just going to sort of mention in passing towards the end of the unit. So our first one is going to be using something called Poissons and Laplace's equations. And we're going to see that our Laplace equation is just going to be a special case of our Poisson equation. And so again, this is going to be our first method. And the reason we're going to pay more attention to this one is it's going to be more general than our second method that we're going to come back to later. And just sort of as a preview to that, that second method we're going to talk about is going to be our method of images. So with our Poisson and Laplace equations, what we're going to start is with our Maxwell's first equation. So as we often do, we're sort of going back to these old equations and we're going to sort of play around with them a little bit and see if we can't get some new relationships. So from Maxwell's first equation, we know that we had the divergence of our electric flux density is equal to our volume charge density. Well, before we write that volume charge density, let's go ahead and adjust this a little bit because we know that our electric flux density D is equal to epsilon times our electric field. And now keep in mind this epsilon is now our updated epsilon that includes any relative permittivities of the material, or I should say relative permittivity, singular. And so ultimately we know that that is equal to our charge density rho sub V. All right, so let's call that equation 1 to be consistent with the notes. And we had another equation from our previous unit that relates our electric field to our voltage. So we know that E is the negative gradient of our voltage. So let's call this equation 2. And so all we need to do now is just substitute this equation 2, so this expression for E here, into our first equation, our Maxwell's law. So if we do that, we have the divergence of the gradient of negative epsilon del V. And so I can pull that epsilon out if I have a homogeneous material. And so let's set that equal to our rho V. And so we can say for the special case of a homogeneous medium, so for homogeneous, and so that of course just means we have the same epsilon value throughout the medium in all directions. So for homogeneous medium, epsilon can be divided out. So only for homogeneous. And in that case, what we get is, and we're going to reduce this a little bit too, because remember, if we have the divergence of a gradient, we had a special operator called our Laplacian. So we have the Laplacian of V is equal to negative rho V, our volume charge density, divided by epsilon. And so this is going to be our Poisson's equation. So Poisson's equation. So now a special case of this would be in a charge-free region. So let's say we have the special case of a charge-free region, which means our charge density for the volume is just going to be 0. And so then we can see that our Laplacian of V is just going to be equal to 0. And so this is going to be our Laplace's equation. And so, as I've sort of alluded to, this is the same Laplacian operator that we've seen before when we were talking about our vector calculus. So you can go back to page 90 in the textbook to see where those equations are, or also in the end cover of the textbook. So those Laplacian operators are given for all three coordinate systems. So remember, we looked at that for Cartesian, cylindrical, and for spherical coordinate systems. So that's sort of the main equations that we're going to be using for this Laplace and Poisson approach. One other thing that I want to briefly mention that the book goes into is something called the Uniqueness Theorem. And so we're not going to go into this nearly as much detail as the book does, but I want to at least point out where it is in the book and sort of state the main conclusion of our Uniqueness Theorem. And so this is in section 6.3 in the book for anybody who's curious about looking a little more into the proofs and all of that goes into this theorem. So basically what we're saying is for a given solution region, so let's say for a given solution region, so if we're talking about in between our parallel plates of the capacitor, and the associated boundary conditions, so and our given voltage that's on the two plates, so and our given boundary conditions, the appropriate differential equation, whether it's our Laplace or our Poisson equation, is going to give us a unique solution. Let's see if I can spell appropriately. So the appropriate differential equation will have a unique solution. And so what we're going to see as we get into some examples is the reason that that's going to have a solution is we'll have some general expression from our Laplace equation. But remember, this Laplacian operator is taking partial derivatives, so to get our v, we're going to have to integrate. And so as we're integrating, we're considering these associated boundary conditions, and those are going to give us our integration constants. And so as we're considering that, we're going to have one unique solution. And so basically what this is saying is, am I just going to come up with some different solution from somebody else following the same technique? And the answer is no. The answer is that there should be one unique solution for a given solution region with given boundary conditions.